Today we are going to finish up chapter 4, our work with derivatives. There are basically three things in calculus: limits, derivatives, and integrals. You now know everything that you need to know about derivatives except for two little things: some odds and ends. All right, so we're going to deal with these odds and ends. One is Lhopital's rule, which is nice and fun and easy. The other one is derivative of the inverse. This is the one that, back a while ago, that was in an AP question. And I said, I'm going to teach you that later. Well, later is now. This is later. All right, so we're going to get that one cleaned off, and then you'll know everything there is to know about derivatives. Sort of. All right, so the first one is called Lhopital's rule. It's named after Lhopital. What's Lhopital's first name? I have no idea. Bob Lhopital. He came up with this idea that if I'm it's for dealing with limits of ratios, limit as x approaches infinity or limit as x approaches 0 of a ratio that turns out to be undefined. I guess what would be helpful is to sort of really look at what kind of problems we're talking about. So let's look at some examples that are like this one: e to the 2x minus 1 minus x over x squared. So this is a limit as x approaches 0. If these were just rational expressions, I would factor them and reduce them, right? Like these limits over here, right? That's x to the fourth plus 2x plus 1. I guess that's not going to factor, so that would be tricky to do. All right, so things that we couldn't do by our normal means of factoring and reducing, like cosine x over sine of 2x, or e to the x squared minus e to the fourth over x minus 2. Like, how am I going to do these with these ln's? Right? How am I going to do these limits? But I have a limit of a ratio, and what I want to notice is what happens if I try to do substitution. I get ln of 1, which is 0, minus 1, times 1, which is negative 1, plus 1 is 0. And then at the bottom, I've got 0 times 0. So this is 0 over 0 if I just go by substitution. But that does not mean that the limit is undefined. The limit probably is defined. It's only the function that's undefined. The function probably has a hole at x equals 1, but it could be well defined. All right, that's the kind of thing that we want to find out. So don't make the mistake of thinking just because the numerator and denominator equals 0 that the limit doesn't exist. The limit very often does exist when the numerator and denominator is 0. The function value doesn't exist, but the limit might. All right, so this is for dealing with limit as x approaches infinity or limit as x approaches 0 of the ratio like that. So if both the limits of the top and the bottom are infinity, or both the limits top and bottom are 0, then something happens. So by the way, we call this, if both the top and bottom go to the infinity, we call this an infinity over infinity form. And if both the limits are 0, we call it a 0 over 0 form. All right. Now, in that case, what you can do to evaluate the limit is just do the derivative of the top and the bottom, and you will have the same limit. So whether it's limit as x approaches infinity or limit as x approaches 0, you're going to have the same limit if you take the derivative of the top and the bottom. So this is called Lhopital's rule. By the way, in your book, you will find this in chapter 8 on page 444. However, my good buddy Rogowski puts it in chapter 4 where it belongs. All right, anyway, so we're going to use Rogowski for the assignment on this. Anyway, so here we go. It says basically that if I want to do some weird limit, I can just take the derivative of the top and the bottom. Now be aware this does not mean that f of x over g of x is equal to the derivative of f over the derivative of x, of g. It's not, okay? So it's not saying that these two functions are equal. They're not. But the limits of the functions are equal. Let me show you what I mean. So we're going to start with Rogowski, number 32. So this is going to be Rogowski, page 246, number 32, and you'll find the Rogowski page attached. So this says limit as x approaches 0 of x squared over 1 minus cosine x. Now here is a critically important thing if you are going to use Lhopital. You have to check to see if you have a 0 over 0 form or an infinity over infinity form. You only can do those two things. Now, by the way, you can learn that there are ways to algebraically manipulate a different kind of form to look like this, but we don't do that in this class. So there are clever things you can do with exponents and things. But we're going to stick with the 0 over 0 form, infinity over infinity form. There are other forms, like 0 times infinity, but essentially you're going to like algebraically manipulate them some way or another to be one of these two forms. Okay, so the first thing we got to do is look at this and make sure it really is 0 over 0 form. So as x approaches 0, what does x squared approach? 0. As x approaches 0, what does cosine of x approach? 1. What's 1 minus 1? 0. So the denominator is also approaching 0. So you want to really, especially on the AP exam free response questions, you want to state that Lhopital's rule applies, because it doesn't apply to everything. Lhopital's rule applies because the limit is a 0 over 0 form. Okay? Most people are not going to want you to write that entire sentence, but at least write that it's a 0 over 0 form. But for the AP exam free response question, I would write out that whole thing, just to be safe. All right, so then what is this saying that we can do? Like, I don't know what limit of x squared over 1 minus cosine x. How am I going to know what that is? I don't know what that is. All right, so here's what we do. We say that's the same as the limit as x approaches 0 of, well, let's start with what it is. Limit as x approaches 0 of x squared over 1 minus cosine x is equal to the limit as x approaches 0 of 2x over, now this is just going to be the derivative of negative cosine x is just sine x, right? Okay. Now, look, when I do this, it's still a 0 over 0 form. If I plug in 0 on the top, I get 0. Plug in 0 on the bottom, I get 0. So it's still a 0 over 0 form. It's not so critical that these are equal to 0. It's critical that they are approaching 0. All right. Because it's still a 0 over 0 form, I can use Lhopital's rule again. So limit as x approaches 0 of 2x over sine x is still a 0 over 0 form. So that limit is equal to the limit as x approaches 0 of, do the derivatives again, 2 over cosine x. Am I getting anywhere? Yes, I am, because look, now you can evaluate by substitution. So this equals 2 over cosine 0. Notice I'm dropping the limit sign now. If I want to be really clear about what I'm doing, that is true by substitution, because I substituted 0 in for the x. And the reason I can do that is because this is no longer undefined. It's 2 over 1, which is 2. Would you have ever guessed that that limit's going to be 2? Well, it is. How do we know that? Lhopital. All right, we'll look at a couple more examples and some traps to watch out for.